Hello and welcome to the course of Heat Engineering. This is lecture 5, Extended Surfaces Fins. In this lecture, we will talk about fins. Fins are a protruding structure to increase the heat transfer rate from a device or object. Extended surface fins. We all know that the heat transfer by convection from a surface through because of a moving fluid can be calculated by using the Newton's cooling law. Q is equal to HA, temperature difference. So to increase the convective heat transfer, we must increase the temperature between the surface and the fluid, that is Ts minus T infinity. Another way to increase the heat transfer is to increase the convection coefficient. For example, using some external fan to improve the convection. Another is to increase the overall contact surface area with the fluid. Fins falls in that category. So what we do, that we increase the heat transfer by attaching some extended surface from an object from which the heat removal is required, and thus exposing it to the greater contacts of fluid. So such extended surfaces are called fin. So now let us perform an analysis of fin based on the energy balance. So suppose you have taken a device or a system whose temperature is TB at the surface, and you have attached a fin or a protruding surface of length L, where let us suppose that P is the fin parameter and cross-sectional area of the fin is AC, and it is constant in this case. We can also have non-constant cross-sectional area of the fin. So now just take a element and perform an energy balance on this element. So energy into this element can be calculated using the Fourier's law, and the energy which exit at x plus dx location can also be calculated. And there are energy also which is leaving this cross-sectional area through the parametric, through the circumference by convection. So that heat transfer can be given as cross-sectional area of the circumference heat transfer coefficient multiplied by temperature difference between the ambient fluid and the local temperature. So if you perform the energy analysis, we will get this. And on simplification, and if you suppose that thermal conductivity and cross-sectional area are constant, then we will get this equation. So this is a differential equation of second order. So we have to solve it to obtain the temperature distribution with respect to x. So now let us define another variable theta, which is varying in x direction and can be given by Tx minus T infinity, where Tx is the temperature at a location x from the base. So this double derivative becomes d squared theta by dx square, and we define our new parameter m like this. So the equation reduced to this form, and now these equations can be solved using the principles of solving ordinary differential equation. So the solution of this ordinary differential equation is of the form of this, where m we know and c1 and c2 are the constant of integration. So there are two boundary conditions we know to evaluate these constant of integration. The first one is the base temperature, which is T is equal to Tb, and the second is the condition at the tip, which depends upon problem. The tip can be insulated. It can be long enough to assume the T is equal to at the tip is equal to ambient temperature, or it can be insulated. So as I have told you that there may be many conditions at the end of the fin, that is tip. So in case first is the infinitely long fin, second is negligible heat loss, means insulated or adiabatic tip, third is the temperature is specified at this end, and the fourth one is that the, that the temperature at this tip can be given by convection, means the convection is taking place at the tip. So based on the boundary condition, we can get the different solution to the above ordinary differential equation. So in this table, we have summarized the temperature distribution Tx, and once we get the temperature distribution, we will get the fin heat transfer also. So if there is a convection heat transfer, that is H theta at the L, means at the tip, can be given by K d theta by dx, means whole of the heat conducted is going out by the convection process. So this will be the temperature distribution formula, and this will be the fin heat transfer quantity. If the tip is adiabatic or insulated, we will get these results for the temperature distribution and fin heat transfer. Similar is the case with other boundary conditions. So we have to memorize all of these results, or we can derive it. So now let us take an example to understand how the concept of fin is used in engineering design. So let us take an example of an aluminum pot in which the water is boiling. The handle size is given and the ambient room conditions are also given. The convection coefficient is given. So the question is asking that whether we can touch the handle when the water is boiling. So we will consider this portion of the handle as a fin attached to the pot, in which the water is boiling at 100 degrees centigrade. So we will consider that the temperature of the base from which the handle is attached is 100 degrees centigrade, and the thermal conductivity for aluminum is known. So first of all, we will calculate the perimeter of the handle and the cross-sectional area of the handle. So M will come from this formula, and so we can calculate the temperature distribution assuming that tip is adiabatic. So from this equation, after the calculation, the temperature distribution in terms of x can be given by this formula. So from this formula, we can calculate the temperature at any location of the fin or the handle. We have also considered that the heat transfer is one-dimensional. Now let us plot the temperature variation along the pot handle. So if we plot it, the base temperature is 100 and it will decrease, and finally at the end it will come to a constant value. So the temperature drops very quickly, and at the end it reaches to a value of 87.3 degrees centigrade. So therefore it should not be safe to touch the end of the handle as the temperature is very high. The total heat transfer through the handle can be calculated by using the formula that comes to the 4.632 watt. So it is very small amount. The amount of heat loss is just enough to vaporize 0.007 kg of water in 1 hour. And for example, if we replace that aluminum handle with a stainless steel whose thermal conductivity is 15 only. So using the same parameters and same boundary conditions and same formula, we can calculate again. So now again using the same formula, we can calculate the temperature distribution. Only the thermal conductivity is changed, and we will get the variation of temperature in x direction as we got the previous. And now when we plot this temperature in x direction, we get that this drop off is not very steep because the thermal conductivity K is quite low in comparison to the aluminum, and the temperature at the end of handle is only 37.3 degrees centigrade. So we can touch the handle. So this is how we have demonstrated the role of engineering analysis in design. So we will prefer the stainless steel in comparison to aluminum because of the safety reasons.